A single teaspoon of a neutron star weighs more than every mountain range on Earth combined. That same teaspoon would crush through the floor of your house, through the bedrock beneath it, and keep falling toward the center of the planet without slowing down. The whole star, every unbelievable ounce of it, could fit inside the outline of a mid-sized city, yet it holds more mass than our entire sun. Some of these stars spin faster than a kitchen blender, completing a full rotation in a fraction of a second. Their magnetic fields are so extreme that, from 1,000 kilometers away, they could wipe the data off every hard drive on the planet at once. Take Mount Everest, the tallest thing most of us can picture, and imagine trying to flatten it with your bare hands. On a neutron star, gravity does that to entire mountains automatically, compressing anything tall enough into a smear only centimeters high. Some of these stars are also among the oldest visible remnants in the galaxy. Dead suns that stopped shining the ordinary way long before recorded human history began, and they are still out there, spinning quietly in the dark, waiting. So, what would actually happen if you fell into one? The honest answer is that you would stop being a person long before you touched the surface. Long before impact, in less time than it takes you to blink, your body would already be unrecognizable. But that first blink is nothing compared to what happens in the final seconds of the fall. Picture yourself in a spacecraft, still hundreds of thousands of kilometers away, coasting toward the star out of pure curiosity. At this distance, gravity feels almost ordinary, close to what a small moon might pull on you, and for a while nothing seems wrong at all. That calm is the trap. Every kilometer closer multiplies the pull far faster than intuition expects, because neutron stars pack a sun's worth of mass into a sphere barely wider than a city. A ship that could orbit peacefully around a normal star would already be losing control here, nudged and stretched by forces that grow in ways ordinary orbits never do. There is no gentle warning line, no obvious boundary where things start to go wrong. If you checked your instruments every hour, the numbers would look almost identical from one reading to the next, right up until they suddenly weren't. The shift is happening underneath the calm, in numbers, long before your body ever feels it. And the moment you do feel it, there will be no mistaking it for anything else. Closer in, somewhere within a few thousand kilometers, your feet and your head stop agreeing on how strong gravity actually is. This is the part almost nobody explains well. Gravity does not pull you as one solid piece. It pulls each part of you separately. And the difference between the pull on your feet and the pull on your head starts to matter enormously. At first, it just feels like being gently stretched on a rack, uncomfortable, strange, survivable. Your spine lengthens by a few extra centimeters. Your shoulders feel like they are being pulled slowly apart. If you tried to swim through it or fight it, your body would resist for a moment, muscles straining against something they were never built to resist. This is the stage where instinct starts screaming that something has gone deeply wrong, even before you understand the physics behind it. The next stretch of the fall is where that screaming stops being an overreaction. If you have made it this far in the story, you already understand this is not a normal kind of danger. So go ahead and subscribe before things stop being survivable at all, because the next stage changes everything about what your body actually is. The stretching now turns violent. Physicists call it spaghettification, a word that sounds almost funny until you picture what it actually means. Your body pulled into a long, thin strand, the way toothpaste stretches when you pull both ends of the tube at once. The tidal difference between your head and your feet, which was uncomfortable a moment ago, is now stronger than the chemical bonds holding your cells together. Bone does not bend gracefully here. It separates. If a person somehow survived to this point conscious, they would feel their spine elongating faster than any injury a human has ever recovered from, joints pulling apart in a straight line toward the star. This is the turning point of the entire fall, the moment where the danger stops being about discomfort and becomes about the complete unmaking of a human shape. Everything that follows only makes this moment look mild by comparison. While your body is being pulled apart, you're also falling straight into a magnetic field that dwarfs anything ever created on Earth. The strongest magnets built by engineers can lift a car. The magnetic field near a neutron star can distort the very atoms in your body, twisting electron orbits into thin cigar shapes instead of round clouds. Chemistry as we know it simply stops working under a field like this. The molecules that make up human tissue rely on the electrons behaving a certain way, and this field breaks that arrangement completely, atom by atom, before gravity even finishes its job. It is one thing to imagine your body stretched. It is another to imagine the atoms themselves losing their normal shape on the way down. By now, your fall has become almost impossibly fast. Depending on where you started, you could be moving at a significant fraction of the speed of light by the time you reach the last few kilometers, covering a distance equal to driving across an entire country in less time than it takes to read this sentence out loud. There's no cushion of atmosphere to slow you here, no friction to soften anything, just empty space collapsing rapidly into solid surface. Everything that took minutes at the start of the fall now happens in the space of a single heartbeat. And underneath all of that speed is heat, an amount of heat that makes the spaghettification and the magnetic distortion feel almost secondary. The surface of a neutron star can reach temperatures in the millions of degrees, hot enough to instantly vaporize anything before it technically registers as touching the ground. If you dropped a block of solid steel toward that surface, it would not clang, crack, or crumple. It would simply cease to be steel, turned into plasma faster than the signal could travel from your eyes to your brain. There is no version of this fall where the heat is not already rewriting your body before gravity or magnetism finish theirs. Somewhere in the middle of all this violence, something even stranger is happening to time itself. Down near the surface, gravity is strong enough that time runs measurably slower than it does far away. To someone watching safely from a ship overhead, your final approach would seem to stretch out, slowing down the closer you got, almost as if the star were reluctant to finish the story. But, from your own perspective, if there were any perspective left to have, the fall would feel like it was happening at completely normal speed, right up until it wasn't happening at all. Two versions of the same event, one fast and one slow, both true depending on where you're standing. Nobody watching from outside would agree with anybody falling on how long any of this actually took. Then comes the surface itself, and here the word surface barely applies. What waits at the bottom is matter compressed so far past ordinary limits that atoms no longer exist as atoms. Protons and electrons are forced together into neutrons, the exact process that gives these stars their name. Whatever remains of a falling object after the stretching, the magnetic distortion, the heat, and the impossible speed doesn't so much land as it merges, becoming part of the same crushed, ultra-dense material that makes up the star. There is no crater, no debris field, no evidence left behind in any form a human mind would recognize as an object. It becomes the star. But even that isn't the true final stage, because there's a threshold neutron stars themselves are not allowed to cross. If enough extra mass keeps falling in, piling on top of what's already there, the star eventually reaches a point where even its own crushed neutron-packed matter can no longer hold the line against gravity. Physicists call this the Tolman-Oppenheimer-Volkoff limit, and nobody has ever watched it happen directly. Past that point, theory says the star stops being a neutron star at all and collapses one final time into a black hole, a place where the physics we've been describing this entire time simply stops applying, replaced by something we still don't have complete equations for. Whether that final collapse looks like a sudden vanishing or something slower, stranger, and still only partly understood, is a question that sits right at the edge of what modern physics can actually answer. Some researchers think the transition could happen almost instantly, the star's surface simply disappearing behind a boundary it can no longer resist. Others think there might be a brief, violent flash of energy released in the process. A final signal escaping just before the point of no return closes over everything, including light itself. Nobody has ever observed one of these collapses directly, and for now, that edge is exactly where the story has to stop. If this pulled you in the way it pulled us together into this fall, subscribe, drop a like, and tell us in the comments which stage of the descent messed with your head the most, because we read every single one.